So far in these programs on mechanics, we've been looking at the motion of a single particle, and we've described that motion by using Newton's second law, mass times acceleration equals force. Now, in this program, we want to look at the motion of systems of particles. So, we're going to introduce a new law, Newton's third law, and the important concepts of center of mass and linear momentum, and the important law of conservation of total linear momentum. Well, all great theory starts off with experiment, so, John.
Well, the experiments we're going to do involve gliders like this on an air track. Now, you've seen this sort of thing before. There's no friction here, and the air track's horizontal, so there are no forces acting on this glider. But instead of one glider, I'm going to look at a system of two identical gliders joined by a spring. Now, if I release this system, you'll see that the motion of either of the gliders is quite complicated. They move to and fro while drifting along the track. And the motion of points along the spring is also complicated. But this special point here that I picked out here with this blue dot moves very simply. To show you what I mean, we're going to freeze the picture to show you after images of this point at equal spacings of time. And you can see from the equal spacing of the after images that the point I marked, it's actually the midpoint of the spring, moves uniformly. Well, why is that?
Well, you can see why that is by applying Newton's second law to each of the gliders in turn. So, in my model, I represent the gliders by particles of mass m1 and m2 at distances x1 and x2 from a fixed origin. Now, what does Newton's second law say? For the first particle, it says its mass times its acceleration is equal to the forces acting on it. Now, these forces are effectively only that due to the spring, which is the extension of the spring, x2 minus x1 minus the natural length, times the stiffness. Now, what about the second particle? Again, mass times acceleration is equal to, and now I also just have the force due to the spring, but now with a minus sign because the spring is pulling in the other direction. Well, these are two pretty complicated coupled second-order differential equations, very nasty, and I suppose that tells us why the motion of each of the gliders is pretty complicated. But notice something. If I add the equations together, because these right-hand sides are equal and opposite, they just cancel out, and I get this very simple equation. In fact, I can make it even more suggestive if I multiply and divide by m1 plus m2. Because if I do that, then you see, here I have, well, I haven't really changed the equation at all, but I can take my double differentiation with respect to time outside, and I just have the second derivative of this expression in the brackets. Now, you may recall that that expression in the brackets is just the center of mass of the two particles. So this is telling me something about the motion of the center of mass. Now, this is the total mass of the system, so I can rewrite this equation as total mass times the acceleration of the center of mass is equal to 0. And that tells me that always the center of mass moves with 0 acceleration, with uniform velocity. But when we have equal masses, when m1 is equal to m2, the center of mass is just the midpoint. And that explains why in John's experiment, it's the midpoint that moves uniformly. But we can actually go a little bit further. First, suppose that the masses aren't equal, but m2 is 3 times n1. For example, m1 could be 1 and m2 could be 3. Then the center of mass is at this point, and that's 3 times nearer to particle 2 than it is to particle 1. So now if we take this system, where one of the gliders has been weighted to make it 3 times more massive than the other, then I predict that instead of the midpoint, it's going to be this point, 3/4 of the way along the spring, that moves uniformly. And so it does. With no external forces, the center of mass moves with 0 acceleration. But what happens if I introduce an external force? Well, the case we had was when the glider was horizontal, but suppose I tilt it, and so I introduce a force due to diluted gravity. So we'll have a component of acceleration down the track, which I've called g prime. Now, what does Newton's second law tell me, for example, about the motion of particle m1? It tells me that mass times acceleration equals the force due to the spring as before, plus now I have m1 g prime. And similarly, for m2, I have the force due to the spring plus m2 g prime. Now, when I add these two equations together, instead of getting 0 on the right-hand side, I'm going to get m1 g prime plus m2 g prime. So when I rearrange, I'm going to get the total mass times the acceleration of the center of mass is equal to this expression, which I can rewrite as mg prime. And I can simplify by dividing through by capital M, and I'll get the acceleration of the center of mass is equal to this g prime. And so what I can say is that this system will go down the track so that the center of mass has the same acceleration as a single particle. Now, when you consider all the oscillations that are going on, it's so complicated, I think that's a very remarkable result.
Remarkable, but is it very significant? After all, Alan based his calculations on Hooke's law. So are we just looking at some special property of springs, or would we expect to see similar behaviour in other systems? Well, actually, Alan hasn't used the full details of Hooke's law. All he's done is use the fact that the spring exerts forces that are equal in magnitude on these gliders, but opposite in direction. So the real question is, if we look at other systems, would we still get forces that are equal in magnitude and opposite in direction? Well, let's do away with the spring and look at these two gliders. Now, there are magnets here, so the gliders repel one another. And when I put the gliders on the track, the midpoint between the gliders represents their centre of mass. Now you can see that the midpoint still moves uniformly, constant velocity, zero acceleration. And that's for the same reason as before. It's because the forces between those gliders are equal in magnitude and opposite in sign. And that's the crucial point for us, because we assume in Newtonian mechanics that the mutual forces between all particles are equal in magnitude and opposite in sign. And that assumption's known as Newton's third law. What we're going to do now in the rest of the programme is explore the consequences of this law, not just in one dimension, but in 2 and 3 dimensions as well.
In 3 dimensions, forces are represented by vectors. So here are the forces on my particles m1 and m2. The force F12 is the force on the particle m1 due to the particle 2, and F21 is the force on particle 2 exerted by particle 1. And I'll also assume that there are external forces knocking about. Well, what does Newton's third law say? In proper vectorial form, it says F12 is equal to minus F21. Now that tells me that the magnitude of these two forces are equal, but the direction is opposed. Now, let me use Newton's second law for these two particles. In vectorial form, mass times acceleration equals all the forces. That's this mutual force plus the external force. And I get a similar vector equation for the other particle. Now, with my experience of one dimension, I know a good thing would be to add these two together. And you see what's going to happen when I do that? I'm going to get the sum of the two mutual forces will cancel out because of this Newton's third law. And all I'm left with, in fact, is this equation, where on the right-hand side I have the sum of the external forces. Also recalling what we did in one dimension, I can rearrange this by dividing and multiplying by m1 plus m2 to get this equation, which is precisely the same as I have above. And now what we have in the square brackets is, by definition, the position of the center of mass. And this is the total mass. So that equation can now be written, well, look at the right-hand side, that's just the total external force acting. And here I have the total mass times the acceleration of the center of mass, m r bar double dot. And so we see that the center of mass obeys a sort of Newton's second law with only the external forces on the right-hand side.
We can see what that means experimentally with this system of springs and pucks. On a sloping table, you may have seen one rather like this in a previous program. Now again, I've marked the position of the centre of mass by a blue spot. And when I launch this system, you can see from the trail of after images that the centre of mass follows a smooth curve. In this case, it's a parabola, which is exactly the same curve that would be followed by a single particle. So in amongst all the complexity of this vibrating and rotating system, there's something happening that's as simple as the shot putting that you saw earlier in the course.
Well, that's one application of Newton's third law. It enables us to make very simple predictions about the motion of the center of mass of a system of particles without having to consider the complicated motion of the individual particles. But there's another very important consequence of that law, and that comes by introducing the concept of linear momentum. So let's go back to our equation for the motion of the center of mass of a system of particles, and this is what we had before. But I want to consider the case now where there are no external forces. So on the right-hand side, I have 0. Now remember, we got that equation by rearranging this equation for the motion of the individual particles. Now I want to look at that slightly differently, so let me take one time derivative outside, and when I do, I get that. Well, you might think that's a silly thing to do, but what I have inside here are velocities, so let me write it in the form of m1 v1 plus m2 v2. Now, this term is called the linear momentum of the particle of mass m1. And what this equation tells me, that the total linear momentum of the system of particles is constant in time. In other words, the total linear momentum is conserved. Now, to say that the total linear momentum is conserved, or that the center of mass moves with 0 acceleration, well, these two statements are equivalent, and they're both true, providing there are no external forces present. But they give us different ways of looking at what's going on. When we think of the motion of the mass, the center of mass, we're thinking of the motion of a particular point in the system. But when I'm talking about the total linear momentum, well, I'm thinking of all the masses and all the velocities of all the particles in the system. And that's a very useful way of picturing what's going on, especially when we're considering collisions.
Let's see how linear momentum can help us with this collision between two particles of the same mass. Now, we've adjusted the table to be horizontal now, so there's no net forces acting on the pucks, and that means we can use the conservation of linear momentum. Now, suppose this particle is the target, and this particle is the incident particle coming into it. Well, before the particles collide, the momentum of the incident particle is mu1, where u1 is its velocity. After it's hit the target, its momentum is mv1, where v1 is its final velocity. And the target itself will move off down here somewhere with momentum mv2, say. Well, now let's use the conservation of momentum. Before the collision, the total momentum is just mu1, plus 0, because the target particle has no momentum. After the particles have interacted, the momentum is mv1 plus mv2. And what the law of conservation of linear momentum tells me is that these two quantities are equal. Now, that's a vector equation, so I can look at its two components separately. And I'm going to take my x-axis along here and my y-axis up here. And I'm going to be particularly interested in the y component of this equation. Now, before the collision, the y component of the momentum is 0. That's because the particle's moving along the x-axis. So it's got to be 0 after the collision as well. That means that the y component of V1 must be minus the y component of V2. These two masses are equal. So now I can make a prediction. I predict that the two particles will cross these two lines simultaneously. Well, that's quite remarkable if you think about it, because what we've done is we've made this successful prediction, but we knew practically nothing about the forces acting between the particles. We couldn't even begin to write down Newton's second law for them. But we could make our prediction on the basis of Newton's third law.
Well, the sort of predictions we can make by using momentum conservation alone are fairly limited. We usually have to make some other assumptions. And a usual assumption to make is that the collision is elastic. By that we mean the total kinetic energy before is equal to the total kinetic energy afterwards. Now that's not a law of nature like the conservation of linear momentum. It's just a rough rule, and it sometimes works and it sometimes doesn't. But it shouldn't be too bad for John's pucks. So let's choose to illustrate this use of elastic collision by reference to an exercise which you'll actually find in your text. So you don't have to worry about the details. I'll go over it rather quickly. The experiment I'm talking about is a glancing collision of a particle of mass m1 off a stationary particle of mass m2. Afterwards, they go off with different velocities, and what I'd like to find out is a relationship between the masses of the particles and the velocities afterwards and the angle theta of scattering. Well, what equations do I have to play about with? There's my momentum conservation equation, this one, and then my elastic collision assumption, which is this one, the kinetic energy before equals the kinetic energy afterwards. Now, what I have to do is to eliminate U1, and it's clear to do that I'll have to square the first equation and then subtract. There's a little bit of algebra involved, but I think you ought to be able to do it for yourselves after the program. Well, when you do that algebra, this is what you get as the final result. You get an expression involving lambda, where lambda is the ratio of the two masses expressed as we wanted in terms of the final velocities. And that dot product actually involves the cosine of the angle of scattering theta. Now I can make a prediction from that. For example, if the masses are equal, so lambda is equal to 1, then on the left-hand side I have 0. And that tells me that cosine of theta is 0, so theta is 90 degrees. So when I scatter two equal mass particles off each other, then they must scatter off at 90 degrees.
And conversely, if we measure the final velocities of the particles after they've collided, well, that will tell us the relative masses of the particles. Now, that may seem a rather eccentric way to measure mass, but have a look at this. This machine, the diagonal line that you see there, is in Stanford, California, and it's really just a machine designed to accelerate particles and launch them into a target. And when those particles collide with the target, they produce tracks like this. Now, when physicists apply the conservation of linear momentum and the conservation of kinetic energy to collisions like this, they can predict the relative masses of the particles involved. Now, what we're doing here on this table isn't really exactly the same as they're doing in Stanford. There are many complications in Stanford because, for example, the speeds are so high that Einstein's relativity has to be used rather than Newtonian mechanics. But what we're doing here on this table is really a good analogy for the best tool we have for probing into the structure of matter. And that's what's done nowadays. But I think it's interesting to go back to the early days of the subject, in fact to 1909, when Marsden and Rutherford and Geiger did experiments by projecting subatomic particles called alpha particles at metal foil. And when they did that, they found that some of the particles came back towards them. Well, when Rutherford heard of that result, he was absolutely amazed. He said it was the most incredible thing that had ever happened to him in his life. In fact, he said it was like firing a 15-inch shell at tissue paper and getting it coming back at you. And the reason he was so amazed is at that time, people really didn't know about the structure of atoms, and they thought the alpha particle should really pass more or less straight through. But let's have a look at the collision now, using the sort of analysis that Alan's given us. You see, the incident particle comes in here, and it's reflected back here. Now, what does conservation of momentum tell us about whatever happens to the particle it hits? Well, remember, the initial momentum was along here, so the final momentum must be along here too. And that means that the target particle must have a component of momentum along here. Then look at the y component of the momentum. The alpha particle is scattered off in this direction, and because there was no initial y component, the target particle must have scattered up here. So the target particle must have gone into the first quadrant, whereas the alpha particle scattered off in this quadrant. And that means that the angle between the final velocities is greater than 90 degrees. And we can deduce that even without looking at this target particle, which Geiger and Marsden and Rutherford weren't able to do. So we now know that that angle is greater than 90 degrees. Let's have a look now at Alan's formula and put theta greater than 90 degrees in this formula. Well, cos theta is negative when theta is greater than 90 degrees, and that means that 1 minus lambda is negative, which, if we remember what lambda means, that means that m2 is bigger than m1. And that's really a historic result. In fact, when Rutherford realized that, he discovered something really important, because what he'd done was to discover the atomic nucleus.
In this program, we introduced the third and final law of Newton, Newton's third law, and we explored two aspects of it. First of all, a very simple equation for the motion of the center of mass, and second of all, the conservation of total linear momentum in the absence of external forces. Now, this law of the conservation of total linear momentum is one of the most powerful results of Newton's theory. And even when that theory has subsequently been modified by relativity or quantum mechanics, this law of conservation of momentum has always remained.